So come to the session 3. The session 3, we are come to the we already know the definition of link integral zero divisor without zero divisors and the properties of a ring and examples. Now the some examples, definitions of ring and properties of a ring. We come to the definitions. See, also no divisor, zero divisor without a zero divisors. See, a ring is called an integral domain. So, integral domains. First, if we got an integral domain, so the ring must be a commutative. What's a commutative means? A plus B equal to B plus A, or AB equal to BA is a commutative. This is a first property is a commutative. You know the definition of unit elements also means unit elements is a unit element without a zero divisor. Without a zero divisor means, see the definition of integral domain is a commutative. First is a commutative as a unit element. Use a unit element without a zero divisor. Without a zero divisor. Is zero divisor? If you take A is an element of A, B is an element of A, product should not be equal to 0. A not equal to 0, B not equal to 0, the product should not be a 0 without a zero divisor. So in this case, is called an integral domain. Integral domain must be commutative as a unit element without zero divisor. This is called an integral domain. First, all this word, set of all Q under addition under multiplication. Set of all complex number under addition under multiplication. Set of all rational number under addition under multiplications. This all. I come to the example of the what is integral domain. We come to the later example. One more definitions. We come to the the integral domains. Now I come to the go for next step. What's a field? See, field is a commutative. Field is a commutative. As a unity, each non-zero element possesses a multiplicative inverses. So I come to the next step. What is the next step means? Is a commutative. Commutative as a unity. Each non-zero element possesses multiplicative inverse. That is called a field. Means a ring of with at least two elements. A ring or in a ring, a ring is non-empty, contain at least two elements. Each non-zero element, A not equal to 0, B not equal to 0. That is the case. A not equal to 0, B not equal to 0. As a commutative, as unity, says that each non-zero element possesses a multiplicative inverse. Is called a field. One more definitions. We come to the definitions. What's in this case? What's a division ring and a skew field? A ring R is at least two element is called a division ring or skew field. If it is as a unity is such that each non-zero element possesses a multiplicative inverse. That is, commutative division ring is a field. Commutative division ring is a field. So we come to that. Every field is a skew field, but skew field might not be a field. These are definitions. This skew field is a division. I come to the again example. We understood what's the definitions between the ring. What's the definitions? What's the difference between the field and skew field? Skew field. So we take an examples of a rationals. See, the set a rational Z form, Q form. So field is 5, Z form. What is Z form? 0, 1, 2, 3, 4. Here, prime. If a non-zero element, we are taking a non-zero. Take elements 1, 2, 3, 1, 2, 3, 4. So here multiply. 1 into 2 equal to 2 into 3 equal to 6. 6 can be written as 1. 3 into 4 we can write here. See in Q 2 is there. Suddenly 1 by 2 is there. 2 into 1 by 2 equal to 1. 1 again. 3 is there. 3 is there. 1 by 3 is there. Suddenly means each non-zero element possesses its inverses. As without means each non-zero element possesses multiplicative inverses. Possesses inverse. That is 4 is there 1 by 4. 4 into 1 by 2. 1 by 4. 4 into 1 by 4. So again you get 1. 1 by 4 is inverse of 4. 1 by 4 is the inverse of 4. 4 is the inverse of 1 by 4. Like that. So product is unity. So inverse is there. Identity exists. The multiplicative It's a commutative. That's a field. So in this case, every field is an integral domain. Every field is an integral domain. Simple proof. See, every field is an integral domain. Yes, simple. Suppose if you take, what's a field? Field is commutative, has a unity. Each non-zero element possesses a multiplicative inverse. Keep it in mind that by using that, we go for proof of giving integral domain is a field. Integral domain is a field. See, since F is a field, F is field is a commutative ring with unity. Must be commutative ring with unity. In order to show that every field is an integral domain, so that field has no zero divisor. Without zero divisor, field has no zero. Means A, B in F elements of a field F. A not equal to 0. If A not equal to 0, suddenly A inverse is exist. A not equal to 0, suddenly A inverse is exist. So A not equal to 0, neither I am multiplying. If A is without a zero divisor, A, B equal to 0. At least one of them is 0. Or A, B not equal to 0. Whatever may be. A, B equal to 0. A, B equal to 0. I am multiplying A inverse on both sides. A inverse of A, B equal to A inverse of into 0. So A inverse of A into B equal to A inverse into 0 is 0. So A inverse into A is 1 into B. So B equal to 0. Any means A not equal to 0, one of the element is 0. I already thought in the definition form. What is without zero divisors, zero divisors? Means A not equal to 0, B not equal to 0, product should not be 0. At least one of them is 0, suddenly is a product should be a 0, like that. Is one of them is 0, the product is 0, like that. So in the other way, in the other conditions, A, B equal to 0, so B not equal to 0. B inverse is exist. B inverse is, I multiply B inverse on both sides. A B of B inverse equal to 0 into B inverse. So A of B into B inverse equal to 0. A of B into B inverse is 1 equal to 0. Simply A equal to 0. Means any one of them is 0. If you take a non-zero element, without a zero divisor, we can write. Similarly, we can prove in the other end like that, but the converse is not true. That means every integral domain is a field, but field may not be an integral domain. Field may not be an integral. I'll give a proof. I'll give an example in the next sessions. See in the next session. See, we prove on the other part the every integral domain is not a field. For example, the ring of integer is an integral domain, but not a field. The ring of integer is an integral domain. Why? The ring of integer. So the ring. What is integer contains? What is integer content? Minus 3, minus 2, minus 1, 0, 1, 2, 3. So what's in field? So minus 1, minus 2, 1, 2, 3 is there. So 1 is there. Okay. 1 is 2 is there. 1 by 2 is in Z? No. 1 by 2 not in Z. So this is the argument. Every integral domain is a field. Field may not be an integral domain. Field may not be an integral domain. This is the field. That is the case. Every integral domain is field. Field may not be an integral domain. Because you take an example Z. Z is set of all minus 3, minus 2, minus 1, 0, 1, 2, 3. So 1 by 2 is there. 1 by 2 is not in Z. 1 by 2 is not in Z. So it's not a field.